Imagine trying to understand a simple container of gas by tracking the exact position and velocity of every single molecule inside. You would be drowning in billions of overlapping chaotic data points. Thermodynamics bypasses this microscopic nightmare entirely. Instead of chasing individual atoms, it looks at the bulk properties of the system, the things we can actually feel and measure on a human scale. You can think of any thermodynamic system as having an identity card. Look at this readout. Instead of a list of 1,000,000,000,000 atomic coordinates, the system's identity is defined by just a few macroscopic state variables: pressure, volume, temperature, and mass. In classical mechanics, you would use math to calculate how fast this entire engine rolls down the street. Thermodynamics doesn't care about the motion of the engine as a whole. It tracks the internal, macroscopic state of the steam trapped inside that cylinder. By reading those few variables, we know the exact state of the steam, and we can calculate exactly how much work it can do without ever observing a single molecule. There is a strict condition for this to work. That identity card is only valid if the system is sitting in thermodynamic equilibrium. If a barrier is suddenly removed and gas rushes freely into a vacuum, the system is thrown out of balance. During that rapid expansion, the gas in the corner of the box is moving differently than the gas near the center. You cannot measure a single, uniform pressure or temperature for the whole container. The exact same problem happens if you ignite a mixture of fuel and air. You create extreme, localized heat spikes and violent shock waves. To study how systems change, physicists rely on idealized models called quasi-static processes. A quasi-static process is an infinitely slow transition where the system constantly adjusts, ensuring it stays perfectly balanced with its surroundings at every tiny step. For our state variables to actually mean something, the gas has to settle. Equilibrium guarantees that the properties are uniform across the entire bulk of the system. Once the gas reaches that stable equilibrium, the numbers on its identity card are no longer independent. They are locked together. In this diagram, we see how they obey an equation of state. For an ideal gas, the mathematical link is PV equals mu RT. The symbol mu represents the number of moles of the gas, while R is the universal gas constant. Because of this strict relationship, if you trap a specific amount of gas and manually force it into a known volume and pressure, the temperature is already mathematically decided for you. The identity card is a perfectly balanced equation. You cannot alter one variable without forcing the others to adapt. Let's test how these specific variables react if we change the physical size of our system. Imagine a perfectly stable cylinder of gas, dropping a partition to slice it down the middle. Look at the data for the left side. The total mass of the gas drops by 50%. The volume it occupies is cut in half. We classify these as extensive variables. Their values depend directly on the physical size of the system. But look at the remaining readouts. The pressure of the gas pushing against the walls is identical to what it was before. The temperature is completely untouched. These are intensive variables. They are intrinsic properties of the material that ignore how large or small the overall system is. If you build a wall right down the middle of your living room, the room doesn't suddenly get colder. The temperature stays exactly the same because it is an intensive property. By identifying which properties scale with size and which are baked into the substance itself, we gained the ability to predict exactly how heat and energy will move through the physical world.